Greetings to all. Today, I am Joshi, along with my colleague Dhiraj, would like to present a paper on generative adversarial network use of non-IID samples. But before that, I would like to thank Dr. M.V. Joshi for his guidance and support. And also, I would like to thank people associated with the conference, respective chairpersons and reviewers for their valuable suggestions, which were of great help. Now let's quickly go through the contents. First is introduction. What are generative models? What is vanilla GAN? Loss function of GAN, variants of GAN, applications of GAN, and then we'll quickly move on to the problem statement and motivation, proposed approach, experimental results, both qualitative and quantitative, and at the end we'll conclude. Now, what exactly are generative models? Generative models are machine learning models that aim to model the joint distribution of both input and output by learning the underlying data distribution. Their aim is to generate samples that statistically resemble the training data. Broadly, there are three types of generative models: NHG-based models, variational autoencoders, and generative adversarial networks. In this presentation, we'll be strictly talking about generative adversarial networks. In the year 2014, Dr. Goodfellow introduced the world with the term GAN, which is now known as vanilla GAN. It basically consists of two neural networks, a generator and a discriminator. Here in the figure, we can clearly see that the generator G is fed with X, which is an IID noise, and it generates an output of Z of G, which is a generated image. And the aim of the generator is to generate an image such that it fools the discriminator. Whereas the aim of the discriminator is to label the generated image as fake and classify the real image as real. And real image is taken from the training data, which is represented by Z of R. Now, for that, we'll go through the loss function. So the discriminator has to take care of two things. First is that it has to classify real as real, which is taken from the training data set, and it has to classify the generated image as fake. So for that, we'll have to maximize the expression expected value of logarithmic of d of zr, where zr is taken from the training data, and expected value of logarithmic of 1 minus d of zg, where zg is the generated image. And in doing, we have to do so with respect to theta, which are the learnable parameters of discriminator. For the generator, it has to take care of only one thing, that is to fool the discriminator. And in doing so, we'll have to minimize the expected value of logarithmic of 1 minus d of zg, where zg is the generated image. And we'll do this with respect to phi, which are the learnable parameters of the generator. Now let's go through the variants of GAN. First is bidirectional GAN. It is a slightly modified version of GAN that also includes an encoder E. So the main aim here is that the encoder E learns the latent code representation of the training data Z of R with the help of the GAN. Now coming on to the auxiliary classifier GAN. In this, we'll be giving an input of both IID noise and class label to the generator, so that generator not only learns to generate image, but also it learns to generate image of a specific type or of a specific class. Now coming to the applications of GAN, the first thing that comes to my mind is image generation. And in doing so, we can also do video generation. Since nowadays in machine learning, we require ample amount of data. So for that, we can produce more artificial data with the help of data augmentation, which uses GAN. And nowadays, many fraudulent activities happen. So in prevention of that, we can use anomaly detection. And other areas in which GAN is used are language generation, image super resolution, adversarial attacks, and adversarial defense. Now, I'd like to request my colleague to take over.
Thank you, Ninad. Now let's discuss about the problem statement and motivation. Here, actually, we have some given a training data. We are proposing one new approach for the image generation, in which the generator takes the non-ID sample as a input, but in that non-ID sample, we are providing some statistical characteristic of the training data. So generator learns much more faster as compared to the new approach. So the motivation behind this problem is the researchers have not attempted to the use of statistical characteristic of the training data while the training the GAN. They use only the IID noise. Also, the using the statistical characteristic of the training data, the proposed GAN is much faster as compared to the new approach, and also it enhances the image generating diversity of the GAN model. Now let's see the diagrammatical representation of the proposed non-ID GAN. Here, let's see the G is the generator, D is the discriminator, ZR is the training data, and ZG is the output of the G. All these things are kept as it is. Just we have changed here y equal to ax, but x is a IID noise, and but a is from the training data set. Actually, basically we are here extracting some characteristic of the training data and providing through as an input to the generator with the help of y equal to xa. Yeah, y equal to ax. So x is IID noise and a comes from the training data set. Now let's see the how to compute that non-ID sample by mathematically. That is the generation of the non-ID sample. First, we model our training data as a one multivariate Gaussian with mean μy and covariance matrix ky. Now we have to calculate y equal to ax, where x is the IID, and our main target is how to calculate this a. So we calculate this from the training data. So now let's come to that point. Here covariance matrix of y is, that is ky, can be written as ky equal to a kx a transpose. This expression comes from this expression. So after that ky equal to a into a transpose, because kx equal to identity matrix. Now ky equal to uy into sigma y into ui inverse. This steps is come from the training data set. For that, we are choosing n number of images. Suppose in particular we choose n equal to 100. So we have n equal to 100 images, and assume each image as a one random variable. So there are 100 random variable in our hand. So calculate the covariance matrix of that 100 variables, random variables. So ky becomes 100 cross 100. But we know that ky is positive definite, so we can express it as a ui into diagonal matrix sigma y into ui inverse. After that, from above two expression, we can write it as a into a transpose equal to ui into sigma y into ui transpose. After some simplification, we get a equal to ui into square root of sigma y. That implies y equal to ax equal to ui into square root of sigma y into x. But this ui and ui into square root of sigma is come from the training data set. So this is the non-ID samples to use the input as a generator. Now let's come to the part experimental result. Here for the implementation we use the MNIST and Fashion MNIST data set, and data set contain, both the data set contains 60,000 training images and 10,000 testing images. All the images are grayscale images of handwritten digits and cloth, with each of size is 28 by 28 pixels. Now for obtaining a, we have choose 100 images from the data set. Per class is 10 images. Now let's come to the part qualitative comparison of the experimental result. Here on the left hand we can see that 16 images generated using the vanilla GAN, and on the right hand side 16 images generated using the proposed GAN. We can clearly see here on the left hand side the generation, the learning the generation of images is yet to start. But on the right hand side, we can clearly see that the learning the image generation is started. That means proposed GAN has head start to learning the image generation, because we are providing some statistical characteristic of the training data to the generator. This is the for first epoch. Now let's come to the epoch number 14, comparison of MNIST data set of epoch 14. Here 16 images generated using the vanilla GAN on the left hand side and 16 images generated using the proposed GAN on the right hand side. We can clearly see that these 16 images generated from the proposed GAN is more diverse and more realness, because here is all the digits are covered, but we can see in we can see in 16 image generated using the vanilla GAN, the some digits are repeated here. We can clearly see that here 1 1 1, this 1 1 is repeated. That means diversity is not maintained, also sharpness is not looking good. So these digits are in the phase of learning phase. So providing some characteristic to the generator, our proposed GAN is much faster as compared to the neo approach. Similarly, for the fashion MNIST dataset, we can clearly see that learning the generation of image is yet to start. But in the case of the proposed GAN, the proposed GAN has one head start to learning the generation of image. So we can clearly see that here our proposed GAN is much faster as compared to the neo approach. Now these are the 16 image of fashion MNIST data set on the epoch 14. We can clearly see that 16 images generated using the proposed GAN. Here these images are more complete and more diverse. But in the case of neo approach, the images are still in learning phase, and also diversity is not maintained here. So we can say that perceptually our proposed GAN is better as compared to the neo approach. Now let's come to the, we saw by perceptually. Now we have to look at the numerically. So quantitative comparison. For that we use the Frenchet inception distance score, that is FID score. The FID score is actually giving us both the things. One is realness, that means how much generated image are close to the training data distribution, and another thing is diversity, means how much variation in the generated images. So FID giving us as diversity as well as realness, and FID is calculated by using this formula, norm of mu t minus mu g square plus trace of sigma t plus sigma g minus twice square root of sigma t into sigma g. Here mu t is the mean of feature representation of the training images, but this mean of feature representation is calculated from the, first we have choose one pre-trained network VGG90. First we are passing the real images, some 1000 real images to the VGG90. After some layer we will get some feature of that images. So take that mean of that features and calculate that mean of the feature representation of the training images. Similarly, pass the generated image by generator to the VGG90. After some layer we will get the feature of that generated images and take the mean of that image feature. So mu g is the mean of feature representation of the generated image. Similarly, we can calculate coherence matrix of the feature representation of the training images, and sigma g is the coherence matrix of feature representation of the generated image, and TR is the trace of the matrix. Now here let's come to the numerical result. Here first column is denoted as epoch 1, 20 up to so on 100. Second column is denoted as FID score of the neo approach, that is FID score for the vanilla GAN, and third column is denoting FID score for the proposed approach. And one thing is note here that lower the FID is the better the diversity and the better the realness. So we can clearly see that the value of the FID score of the proposed approach is lesser as compared to the neo approach. That means providing the statistical characteristic of the training data, our proposed GAN is much faster as compared to the neo approach. Now, this is the FID score comparison at various epoch for the fashion MNIST dataset. This comparison is for the MNIST dataset. Now, this is the comparison for the fashion MNIST dataset. So, we can clearly see that here the FID score of the proposed approach is lesser as compared to the neo approach. That means our proposed approach giving FID score is lower, and we can FID is lower, so we can say that it proposed approach has more diversity and more realness. Now let's conclude this session. In this paper, we proposed a new approach which generator is fed with the non-ID sample, but that non-ID sample is derived from the training data. Also, generator learns to generate new images much faster than the new approach. But in the new approach, they are using ID noise, but here we are using non-ID noise. So generator is much faster as compared to the new approach. So proposed approach increase the more diversity of the gain, which is demonstrated on the MNIST and fashion MNIST dataset with the help of FID score. Thank you.